Okay, so picking up where we left off from yesterday, so we were talking about fractions. We're trying to find least common multiples. We're finding out the rules to add and subtract, multiply and divide said fractions and all those guys. We did go through some terminology. Any questions about the terminology or, like I said, the math that we were dealing with yesterday? Okay, so today we are going to start into adding and subtracting fractions. Now, the reason that this is important is because a lot of what we do and a lot of the equations that we form end up being in some sort of a fractional form. We have different bits and pieces. So we have to be able to understand how can we convert these guys back and forth to add and subtract fractions. Because there's going to be lots of different things, especially when we get into using Kirchhoff's voltage laws and current laws and loops and everything. We're going to create problems that have lots of fractions. We're going to be substituting stuff in and out. And to combine everything together to simplify it, we're going to be needing these tools. So the first step that we have to do in converting or in adding and subtracting fractions is we have to get the denominators to be equal. That's the first step. So once we do that, then we're going to use our least common multiple, because again, that's going to reduce the amount of reduction we have to do at the end of the thing, less chance for making errors, things like that. So like the rules that we have, so if we start with 5/8 and we want to add 9/15, we need to figure out what that equals. So when you just plug these into your calculator is going to automatically do this kind of stuff. So that we're understanding more of what our calculator is actually doing. So we need to find a value that both our 8 and the 15 will go into. Or if there's an easy way, we can add these together. Now, we can't use our cross multiplication because we're not multiplying. We are adding. Okay, so in this case, we want to kind of look at, there's two ways we could do it. We could just do a brute force method, multiply 8 and 15 together, and that will give us a value that they will both go into. But we want to see if there's a smaller one just to help reduce it later. So when we have an 8, that splits up to 2 and 4, and then 2 and 2. Our 15 is 3 and 5. So in this case, looking at it, do we have an option for a least common multiple that is not 8 times 15? No, we do not. So in this method, the brute force is going to give us our best option for that. Okay? So in this case, we're going to multiply those together. We just want to check to see if we have an option for that. So we have 8 times 15. So that's going to give us a denominator of 120. So we need to convert this guy. And it's going to give us some answer over 120s. So for the 8, since this is our lowest value, what do we have to multiply by the 8 to get the 120? The 15. Okay? So we have to multiply this both by the same thing to maintain it, because 15 over 15 is the same as 1. And if we're multiplying it by 1, we're not changing the equation at all. Okay? So now we take our 15 by 5 times 5, and that gives us what? 75. Okay, now we got to look at our second value. We need to multiply this value by what to get 120ths? 8. 8 over 8. So multiply numerator and denominator by 8. So we end up with what over 120 for our second digit? 72. Now we simply add those two together, and that gives us So it gives us 147 over 120. Now, for all intents and purposes, that number is correct. Okay? Depending on how we want to go at this point, we can either keep it in fraction form or we can reassign it and put it into a mixed number, where we have a whole value, we have a decimal. We have the leftover fractions. Or we can convert it to the decimal. It just depends on how we want to use this number. Most of the time, you know, for these questions, we're going to leave it as that. There may be some times where we want to convert it to a decimal, things like that. Huh? Sometimes. For us, for all intents and purposes, that value is perfectly acceptable. And usually if we do simplify it down, we're just going to put it down to a decimal value anyway. Any questions about that? Okay. So would this, though, simplify down? Like you were saying, would it simplify down? What does it come down to? 49 over 40, and how did you find that? Okay. So in the way, yes, you can simplify this down to a number, but this is an acceptable answer. Would you say 49? You can reduce it down. Both of those are acceptable. A lot of times, like you said, I was thinking converting it to a mixed number. That's what I was thinking. So if you can simplify your answer, do it. And what, like I was saying, one of the reasons here is where we want to find the least common multiple, is that's going to reduce the amount of reduction we have to do at the end. So I know it's kind of a little bit of redundant words, but anything to kind of save us a step on the end, what we have to do to manipulate our answer, you know, might as well work it into when we're solving the rest of the equation. Okay. So we've got another one, 16 33rds, and we want to add 9 11ths. Okay, one way we could be thinking about this is we could have, these are currents that we're trying to add together, for example. Trying to find out how much total current we have in the circuit. Okay, this could be 16 volts, this could be 33 ohms. So this is where one place where we would be using these fractions in actual applications for our math. So we're going to end up with a current plus a current, and that's going to give us a total current. Just as an example of when we would be using these types of things. So first thing, what is going to be our common denominator? 33. Because both 33 and 11 will go into it. So we need to convert these guys both to 33. What do we have to do to this first value? Nothing. It's already there. Okay, when we get back to the next term, what do we need to do to that one? Multiply it by 3. Or multiply both parts of our fraction by 3 to be more precise. Okay, so this turns into 27. Now we have the same denominator, and the cool thing with this is we now have 33, we have 16 plus 27. So we can combine them together even to one fraction. That comes out to be 43. Will that reduce down any farther? No. So like I said, when we get into a lot of these equations where we're building new equations, a lot of times this is what we're going to run into. We're going to have to add and subtract in mixed values, so we have to convert them in one way, shape, or form into something that's the same, so then we can treat them together. Because even just looking at them in the end, you know, 16 over 33 doesn't mean a whole lot. But suddenly when we look at it as 16 volts over 33 ohms, hey, I know what that is. I can deal with it. That's what we're trying to solve for. So that's the idea behind this is we kind of do this instinctively, but this is the math behind it. This is why we're doing it. Okay, any questions about that? Everybody feel pretty good, pretty comfortable with those? Okay, they're going to get more complicated than this as we go along, just so you guys know. Mixed numbers. What are mixed numbers? Yep, a whole decimal number and a fraction. So, let's say we want to do some math back and forth. Let's say we want to add 8 3/4, and we want to add, I don't know, a quarter. Let's say we're cutting something for our projects. we know that we need whatever we're measuring for. We need to be 8 3/4 inches. Then we need to add a 1/4 inch for our saw blades when we cut on the end to make sure it fits. How are we going to, actually that's not a 1/4, let's do an 1/8. Let's make this something we actually have to convert. Okay, so now we have 8 3/4 and we need to add an 1/8. Okay, well what's the first step that we need to do? Yeah, we need to convert this number back to a fraction. Okay, so when we do that, if we have to look at how many holes we have and how many parts of the hole do we have. So the easiest way to remember is take our whole number, multiply it by our divisor. How many pieces are we looking at? So we have 8 times 4, and then we have to add the remaining of what was left over the piecewise. So 8 times 4 is 32, add 3, it's 35. So now we've got 35 quarters, 35 fourths. We want to add an extra 1/8 to it. So the next thing we need to do is convert these guys into the same common denominator. And in this case, what is our common denominator? 8. So in this case, we have an 1/8. That's going to stay the same. Now what do we have to do to this guy to go from fourths to 1/8? Multiply it by 2. Then, so 35 multiplied by 2 is 70. And then we add these two together. Okay. In this instance, yes. Okay, so when the question asks for it, it'll say convert it back into a mixed number. So now that we got 71/8, now we need to divide it out. And how do we do this? How do we convert this back into a mixed number? Okay, how do we do that? Throw it in your calculator. Easiest one. Okay, so 71 divided by 8 is what? Okay, so we know right off the top we're going to have 8 holes. And 875, that is, any guesses? 7/8. So this is going to convert down to 8 7/8. So one of the cool things that we're going to, we'll show you guys as you get into these, you're going to start recognizing different patterns that are going to emerge based on your decimals. If you can pick them up. What's the decimal for an 1/8? 0.125. What's the decimal for a 1/4? 0.25. Okay. Some of the things you'll start to notice is because we'll use 8 a lot, especially once you guys start getting into binary and octal and those different number systems. You'll start seeing these conversions coming out really, really fast, going back and forth. In the end, we could have had our calculator. A lot of the calculators will spit this out into a mixed fraction. There's usually a function in there. The TI-83s, you have to go into the math menu, and then you select number, like the arrow going to a fraction, and then it'll convert and display it as a fraction for you. I think the TI-38s will. I think there's a button for that. The Casio, I know, will. That one will go back and forth between mixed and improper fractions and decimals, things like that. So when it comes to those, like I said, a lot of this is going to be based on your calculator, using that, but this is how you can solve them without. Some of the stuff we're going to get into is I think, next week or the week after, I believe we're going to be getting into division of polynomials. That's fun. Lots and lots of terms that we're going to divide in and out. And all it is just to show you this is where these values are coming from. This is understanding the math behind the formulas that we use. Okay, any questions with this? With mixed numbers converting back and forth? Okay? So one of the next things that we're going to do is we're going to go into a little bit more of conversions back and forth between different engineering notation values. So if I have the value 800 milliamps, I want to know what it is in amps. Okay, so to start with, milli is what? After the decimal, so 10 to the negative third. And amps is 10 to the 0. Okay, so just like the rules we've been learning before about converting numbers back and forth between power of tens, if I want to go from milli to amps, I'm going to be increasing my power, so I have to decrease my number. Basically, I have to make it a smaller version of it. So how many spaces am I moving? 3. So I got to adjust this back 3 decimal places, and we get 0.8 amps. Okay, let's say I have the same value, 800 milliamps. I want to know how many nanoamps that is. Okay, so milli again is what? What power of 10 is it? Negative 3. Nano, negative 9. I have to stop and think about this through my head. So it goes milli, which is negative 3. Micro is negative 6. Nano is negative 9. Pico is negative 12. So, like I said, going down through pico, up through gig, even into tera a little bit is where we're going to be our ranges. So in this case, I'm going from a negative 3 to a negative 9. So am I getting bigger or am I getting smaller? Smaller, because it's negative. Yes. Yes. So because this number is getting smaller, this number has to get bigger. So we're going to move over how many decimal places? 6. Yes. The smaller your power, the bigger the main number is going to turn into, and then vice versa, depending on where you're starting from and where you're going. Yep, so 800 milliamps is 800 million nanoamps. And again, that's just kind of hard to say, but there's sometimes you want to compare things, compare them in the same units. So you can quickly go back and forth. Okay, what if I had... If I'm going from 0.875 kiloohms, how many ohms is that? 875. Because again, we're going from 10 to the third to 10 to the 0. So we're decreasing. So that number has to get bigger by moving the decimal place over. Another common one that you guys are going to see is 10,000 microfarads is equal to how many farads? 0.01? Okay, so we're going from 10 to the negative 6 to 10 to the 0. So we're moving 6 decimal places. The number is getting larger because it's getting more and more positive. So we come up to 0.01. This is what you'll see in capacitors. There'll be times that they're going to be rated in microfarads, and we have to determine, it comes up. Another common is you'll see 0.001 microfarads, and we want to know how many nanofarads that is, just to give us a comparison number, an easy one to put in. Because this is kind of hard to look at because you're micro and you have a decimal value. Why not convert it into like a whole number in one of our engineering prefixes? Yep, 1 nanofarad, because we're going to move this in 3 decimal places. Capacitors do that a lot. They give their ratings for capacitors in usually microfarads or picofarads. And you have to convert it back into back and forth to get their actual value. Which is kind of silly that they do it, but that's just the unit of measurement they decided it's to be measured in. Plus the measurement tools that we have for capacitors, it only displays answers in microfarads or nanofarads. So it doesn't give us anything in between. Or picofarads, not nanofarads, sorry. It'll give you a value in picofarads, and it would usually be 1,000th value if it's in the nanos, and then vice versa. Sometimes it'll be 0.00 something microfarads, and it's in the nano range. So get comfortable converting these back and forth. We're going to see this one a lot. A lot of your guys' meters, this is how it displays the answer. 0.875K. Make sure you pay attention. It will give you a little symbol in the top row of your DMMs if you're in kiloohms, or even if you roll into mega ohms, you'll still see the same thing. If we had 0.875 mega ohms, that's how many kiloohms? 875 kiloohms, and that's also 875,000. Yeah. Yep, 200K, and then your next one is 2 meg. So these conversions are going to go back and forth. A lot of times we're not going to have to like convert from meg into micro, but we can if we really wanted to. That's going to move it, 9, 12 decimal places. The biggest thing is remember going back and forth in between these engineering notations is that it's in groups of 3. It's always groups of 3. It did. Okay, any questions about converting back and forth between values? So there'll be times when you guys are giving me answers and things like that. So you might give me an answer that says 0.033 kiloohms or whatever, because maybe that's what your calculator gave you or something like that. I might just convert it to 33 ohms. So going back and forth with that, make sure you understand what those conversions are. Or if you miss something or you didn't quite catch it, ask. Be like, wait a minute, I thought that was in kiloohms. Well, it is, but we can convert it down to ohms. Make sense? Okay. That takes care of a lot of the math for today, just strictly the math. So now we're going to dive into series circuits. What can we do with them? How do they work? How can we get them to, to behave? How can we calculate values, that type of stuff. So what we're used to seeing right now is we are used to seeing a single voltage source and a single resistor. Okay? This is good. This is a great first step to understanding series circuits. But what we want to do is we want to be able to set this up to where I can have, whatever voltage is coming out, whatever I set it to, but I want to be able to select a voltage for some sort of a use, okay, whatever it may be. So in this case, this is what we're trying to get down to, because this is the simplest series circuit that we can make, is one supply, one resistor. Anybody have any questions on how to solve Ohm's law using this guy? Pretty basic? Okay. What we have now is we have situations where we have multiple devices. So for example, this. What's that indicative of? What component in the lab have we been using? A potentiometer. This is what our potentiometer is doing. It is establishing 2 separate resistances to be able to solve for this. Now outside of the potentiometer, we have the option to separate this point to get different measurements. But just kind of going with the potentiometer right now, we're going to leave this connected because we can't physically break where the potentiometer is and connecting our wires. So in this case, we now have 2 resistances. And what have you guys been finding as you've been experimenting with the potentiometer? What happens when you measure across A and C? You get the full thing. Well, what happens if I set this to 30%? What happens between A and C? You get all of it. When you're looking across everything, you get the full total amount. The wiper arm is only establishing how much a ratio of where these guys are going to be. So for example, in the circuit, we have an R total, which is equal to RAB plus RBC, R1, R2. Think of it that way. We have two individual resistors at this point. When they're in series, and what does series mean again? One current path, okay? We come into the component, there's only one direction. We go through the component, when we come out, there's only one direction. We go into the next one, come out, there's only one path. So remember, a series circuit is one single current path. Our resistance total is going to be everything in series added together. Make sense? So now we have that, we can find our current total. And what's the rule about current in a series circuit? It stays the same everywhere in a series circuit. So that means we could put an ammeter here, we could put an ammeter here, and if this wasn't a potentiometer, we could put an ammeter there. All three of those, if we had them all hooked up at the exact same time, would give us the exact same current. Now the difference is we're going to have different voltage drops. Okay? So as we were talking about yesterday with Kirchhoff's voltage law, whatever voltage we have coming in has to be the same voltage that is being dropped or being used on our output. So with this, when we solve for these currents, so we can solve for our current with that formula. That's equal to the current through RAB, and that's equal to the current through RBC. We can find the individual voltage drops across these guys by just simply using Ohm's law. So voltage is what? What's the formula for voltage? Current times resistance. So the voltage from A to B is equal to the current total times the resistance from A to B. The voltage on our resistor B to C is equal to the current total, or the current going through that component, times RBC. And like I said before, we can label these however we want, just as long as we're consistent in our problem for how we're labeling them. In this case, I'm just labeling it AB because those are the 2 points it's connected to. I could label that one R Bob if I really wanted to. Yes?
So then the current going through RAB would be 70%, and the current going through RBC would be 30% of that?
The voltage.
Or the voltage, yeah.
The current's going to be the same. So yes. So if we have this set up to where RBC is 30%, that means we have 30% of our R total, we have 30% of our voltage total. And that's one thing you guys will start to see in this other lab, and that's what you should kind of see when we're going between 100% and 50%, just a couple of set points. In the quiz, we're going to be changing that percentage. And that's all you're doing is looking at this into a complex series circuit. Now the idea behind this, yes? Yes. Yep. So now, let's say we get away from using a potentiometer, and now we're going to use two resistors. It's going to follow the exact same plan as this. The only difference is we're not going to have a set R total. It's just going to be the combination of what our values are. But it's going to work in the same way as the resistor or as the potentiometer does. So to start with, we have our circuit. We have R1, we have R2, we have 10 volts. This guy is 1.1 kilo ohms. This guy is 2.2 kilo ohms. So when I'm looking at this, I need to find my R total, my I total, my voltage across R1, voltage across R2, and power. One of the things that's very important that we're going to get into is with the power is we need to know how much power is going through this guy, because we need to understand how big of a resistor do we need to put in there size-wise to handle it. The ones that you guys have in lab, I believe, are 1/4 watt that came with the kit. I think it says that on the package what they are. That means they can handle up to 250 milliwatts of power. So when you're building a circuit, this is important to know so that way we can put the correct size in there. Because if we don't, it's going to burn up, or at least get hot, and it could burn you, even if it doesn't burst into flames. Okay? So first example we're looking for is R total. R total is going to be a combination of all the resistance in series in this circuit. So we have R1 plus R2, which comes out to be 1.1K plus 2.2K. So when we add those together, how much resistance does that give us? 3.3K. Now remember when we put answers and when we're doing our math, put in the units and the symbols in there. That way it'll keep you from making dumb mistakes like what I used to do in high school. I multiplied volts times volts to get ohms. Instead of volts times, I don't remember exactly what I was looking for, but yeah, I did volts times volts to get ohms, and my teacher mocked me profusely. It was great. Okay, so we now have our R total. So that's the total resistance of this entire circuit. Our current total is going to be the voltage total divided by our resistance total. So we have 10 volts divided by 3.3 kilo ohms. And that's going to give us how much current? Everybody good with that? Agree with that? Know how we got that? .03 milliamps. So that's our total current going through there. That means that's the current going through R1. That's the current going through R2. That's the current going through this wire. And that'll come into important later on because depending on the gauge of wire you have, it's how much current that it can handle. A lot of the stuff that we use can handle, it can handle several amps of current, even just these little itty bitty wires. The power supplies that you guys see in building in third semester, those ones have just the regular size wires. I think it's 20 or 22 gauge wire, and they're able to handle an amp or two of current. They can handle it. The stuff that you have in your houses, it's 12 gauge wire if it's 15 amp. It's 20 gauge wire or 10 gauge wire if it's 20 amps. So the more current, the thicker the wire has to be to keep it from getting too hot. So we have that. Now we need to find our voltage drop across R1. So to find voltage, which formula do we use? Current times resistance. Okay, so in this case, our IR1 is going to be the same as the total. And then R1 is 1.1K. So the voltage across R1 comes out to be what? Does that answer make sense? Okay, because 1.1K is how much percent of 3.3K? It's a third. It's 33%. So we take 33 times 10, we get the 3.333. Exactly. So VR2 is equal to the voltage total minus VR1. So 10 minus 3.333 to the 6.664 volts. Now, let's double check that. Make sure that's what it's supposed to be. Let's use our current to solve for it. So VR2, we're going to use the same formula, IR2 times R2, so the 3.03 milliamps multiplied by the 2.2 kiloohms. What does that give us when we punch it into our calculators? Yep. It better. Okay. So with the simple series circuits like this, we can design circuits to give us a certain current, and then we can also design it to be able to give us certain voltage drops off of these resistors. So if we had different motors or things that we wanted to use for it that require a different amount of voltages, we could do it this way. Yes?
So that's the kind of voltage drop is the correct amount of voltage, correct?
Yep. Because we're going to use it for something. Any questions about this? Good? Okay. So one of the things that we can also do is we have another formula that we can use to solve this guy without having to get into the current. Some people like to use current to solve for everything, and there's times and places where you do use the current to solve for it. There's other times that if we don't necessarily care what the current is, for whatever reason, we know it's not going to be a whole lot, we know we're not going to be in trouble with power, sometimes we just need to know what is my voltage drop. So if I'm testing a circuit, I can find out what is my voltage drop so I can test it real quick to see if it's working correctly. We have a formula that's called voltage divider. This works great for DC power. AC power, it starts to become a little iffy, just because now we have phase angles that we have to worry about in AC. So this works great for DC power. The voltage divider simply is, if you want to find the voltage of whatever resistor you have in series. So that's the biggest thing. Voltage divider is series only. This formula will not work for a parallel circuit. So the voltage drop of whatever resistor we want is going to be equal to the voltage total multiplied by the value of whatever resistor we're looking for. So in this case, R1, R2, RBOB, RBA, whatever it is that value over the resistance total. So if we were just to go back and look at this formula without having to calculate the current, we could find the voltage drop across R1 by going 10 volts multiplied by 1.1K over 3.3K. This is going to reduce down to 0.333 multiplied by the 10. And we end up with our 3.333 volts again. So there are times when it's easier to use voltage divider for a real quick and dirty look to find out what are my voltages going to be. And then from there you can calculate your currents. From this point you could go through, you'd find that your VR1 is this, your VR2 is this. You can then take that voltage, either one of them, divide it by those resistors to get your current. And then because they're in series, you know that they have to have the same current. Make sense? Okay? So some of the rules that we have for a series circuit. So one current source, or one current path, the current for Rule 2 is the same in series and the last one is voltage drops must equal source voltage. Okay. No? Hey, we're back. That was weird. Wondering if I bumped one of those controls down on the bottom.
You have to choose certain resistors in order to add up to the voltage total, or
You can split it up however you want. So depending on if you want a specific current or you want a specific voltage, then that kind of decides your design process. And then the fourth one is our voltage divider. That's where this works. So the rules for series is one current path. The current is the same through all parts of that series network. The voltage drops must equal the source voltage, and we can use voltage divider. Like I said, voltage divider will not work in a parallel circuit. We have another formula that we use there. Questions about series? Okay, so let's get on kind of going off with your question. Let's get into a design problem. Okay, so using Ohm's law and using everything that you've learned so far about series circuits, I have a battery. I have a 9-volt battery. I want to build something that is going to split up my voltages in such a way that I get 3.3 volts on one of those. So for example, I want to have, I'm just going to use this as a resistor right now, not to confuse you guys, but I want to have an LED that turns on when this is connected up. The LED is going to drop 3.3 volts. The rest of it, I can drop across this resistor. So in this scenario, I only care about this voltage. The rest is going to go over here. So it's up to you guys to figure out how am I going to set up this ratio. And I don't really care what my current is. Let's just say, as long as I have more than 10 milliamps, I will be happy. So looking into this, we've got two resistors that we need to determine in order to build this circuit. Okay? Step one, where do we go from? What do you guys thoughts? Okay? How are we going to do that? Okay. So the voltage drop across R2, that's probably something we're going to need to know. That is going to be equal to the 9 minus the 3.3. So I know, just off the information that's given to me, I'm going to have 3.3 volts dropped across here, and I'm going to have 5.7 dropped across R2. Now where do I go? Okay, we can do that. So how do we do that?
Divide 3.3 by 9, and then multiply the result by 100, their percentage total 36.6.
Okay, so we need 36, almost 37% of our total resistance on that resistor. We need the rest. No, I think I'm hitting a button. No, I don't want you to power off. The hell? I'm not sure what I'm hitting down here. Okay, so there's my ratios. I know I need, for my total resistance, I need to have 36% of it up here, and I need to have 64% of it down there. Okay? So what other piece of equipment did I give you guys? A minimum current. Okay? So I want something that's greater than 10 milliamps. So pick one. If that's the only constraint you're given, pick one. 10.1 milliamps. Sounds good. So we're going to design this so our current is equal to 10.1 milliamps. Okay? This is one way we can go to solve this. If we don't care what the current is, we could just solve for it and figure out what the resistors need to be, and then we can adjust them. If we have too much, we just put in smaller resistors, but we maintain those balances. Okay? So we have 10.1 milliamps. Now what do I do to get those resistor values? Ohm's law. So R1 is equal to voltage of R1 divided by the current through R1, which is 3.3 volts divided by 10.1 milliamps. What do we get for a value for here? You didn't take into account the milli. Yep, 326. So R1 is going to be a 326 ohm resistor. R2 is the voltage drop across R2, the current through R2. So 5.7 by the 10.1 milli. Yep, that's what I was thinking. I think you did probably 0.011. Oh, yes. So we end up with, we need a 326 ohm resistor, and we need a 564 ohm resistor. So now we built this circuit to give us exactly what we wanted. Okay? The cool thing is when we get into LEDs and stuff, this value here, so like we plug the LED in, it's going to drop that much. Internally, it's going to change to whatever it needs to give us that 3.3. So then we just have to worry about getting this and then giving our current controls. So that's one of the cool things with LEDs. But for here, if we didn't really care what our value was. As long as it's something over 10, we're good, because that was the only parameter we were given. We could go back through and we could plug these values into our voltage divider. Okay, we have the formula. So VR1 is equal to R1 over R total multiplied by the voltage total. Okay, so we know this is going to be 3.3 volts. We know that this ratio is going to come out to this value, so we have to kind of play with it. We need to give us a value, we need to pick some values that are going to give us 36.667%. So we could pick any resistor value at this point. So let's say we wanted a total of 100 ohms for our total. So now we need 36.667% of 100 ohms gives us 36 ohms. Okay? So then that one would then be 36 ohms. This would be 64 ohms. Okay? We still are satisfying this value here of greater than 100 or 10 milliamps of current. If we have 9 volts divided by 100 ohms, what's our current? .09, 90 milliamps. Is 90 milliamps greater than 10 milliamps? Yep, so we've satisfied that requirement. So when we're designing these, look at everything that we have. And we can either go, like we said, this direction and just arbitrarily pick a current that we want to get to, or we can arbitrarily pick a resistance total as long as the total current doesn't exceed our specifications. And so each of the design parameters are going to be a little bit different depending on who's asking the question, what are we building it for, things like that. Because there'll be times, well, you'll be given a manager will give you this problem, and they're like, I want this with these parameters. And they're going to be like, you know, you could give them this, and they're like, I don't want to use the 326 ones. Those cost 4 cents. I want something cheaper. So you can come back through and you find, oh, a 36 ohm resistor costs 3 cents. So sometimes you have to adjust your design based on what what the person giving you the question is looking for. But a lot of times when it comes to these, you're going to be pretty much, I want a circuit system to do this. These are my minimum requirements. Go to town. So in this case, so this ratio right here, this is the 30. That's the 36.667. So we know that this value here has to equal this percentage. I arbitrarily decided I wanted to pick our total to be 100 ohms, just to make the math simple. And I knew that if I had 9 volts and 100 ohms, I'm going to have more than my 10 amps or 10 milliamps. So because we don't have an R total. So we have to pick one, keeping in mind this constraint. And I knew 100 ohms and 9 volts would give us plenty of current. So at that point, it just kind of becomes an arbitrary assignment of how you want to design this. So there is no right answer, per se, for this. The right answer is, does it meet this criteria, and that criteria? That was all that was given. Does it meet it, yes or no? Then a lot of times, doesn't matter how you get there. But there's multiple ways and multiple routes to get to the correct answer. And in this case, it's a correct answer, because there is no specific one answer. Now, if I would have given you, I want 40 milliamps, then you have to meet that constraint, so then this no longer becomes arbitrary. You have to design it to build that. So in this case, if I had said I wanted 40 milliamps, how much resistance do I have to have in the circuit to give me 40 milliamps with 9 volts? $225 ohms. So then this becomes 225 ohms. Now I still have those same ratios. It's just based off of 225 instead of 100. So a lot of these, especially when we get to the projects near the end of the semester, is I'm going to give you guys values. And some of the other ones, if I don't necessarily specify it, I don't care. I don't care how much current you have. I don't care, what the voltage across your shunt resistor is. Don't care. As long as you meet what I do care about, that's what I'm expecting. And that's, when you get into the job field, that's what's going to be coming. A lot of times I don't necessarily, depends on the situation, but there was times we were fixing tools up at ON. They had been down for a week. It got to the point where the manager said, I don't care how you get this thing fixed. As long as it's safe, we don't void any warranties, nobody gets hurt, get it fixed. So there would be times we would have to get creative. There was sometimes for a temporary fix until we could get a circuit board in, we would reroute power from one location to another location to power this component because that's all we needed. Until we could get a power supply in, we would bypass it. And so we would get it fixed because we had to get product moving. If we didn't get that stuff moving, the entire factory was going to shut down. And it happened on a couple occasions that we had tools down that they actually sent all the other workers in the fab that were loading the tools to break for 6 hours until we could get the tool fixed. Because there was nothing they could do. Because nobody could move any product because the product in front of them wasn't moving. And there was no reason to build up this huge bubble to where now all of a sudden, you know, they got this bubble in the line and it's going to mess things up, mess metrics up, all sorts of stuff. So there's times that you just have to get things done and they don't care. There's other times that they're going to lay out every little step that they want you to do. And you guys are going to get a mix of that. Okay, any questions? Okay, let's go ahead and go to break. And then when we come back, we'll do some more of these and then we'll start getting into designing voltage supplies. Voltage meters.